Okay guys, we're having a look at measures of centre and spread for a discrete random variable DRV part 2. Today, measures of spread. Alright, let's get going. Measures of variability or spread, variance and standard deviation. That's what we're dealing with today, variance and the standard deviation. Both are very, very similar to each other in terms of how you work them out. Now, the variance of the random variable x is a measure of spread of the probability distribution about its mean or expected value. It is defined as var x equals the expected value of x minus mu all squared, and may be considered as the long run average value of the square of the distance from a value x to mu the mean. Okay, so the variance is usually denoted this symbol squared, where this symbol is the lowercase Greek letter sigma. Sigma. Okay, that's lowercase sigma. All right. The capital sigma is that funny big monstrous looking thing that we use for the sum of. Okay, and you'll see that in a moment, just out of interest. Now there it comes. So from the definition, var x equals the expected value of x minus mu all squared, which is the sum of, there's your Greek capital sigma, it's the sum of all these values of x, take away mu, square it, and then multiply by the probability that your DRV equals that specific value of x that appears here. Okay? Now, that looks like total and utter algebraic mumbo-jumbo, but we will show you how to do it and you'll see. Okay, so fear not. Now, since the variance is determined by squaring, see this, squaring the distance from x to mu, it is no longer in the units of measurement of the original random variable because it's the square of it, right? So a measure of the spread in the appropriate unit of the DRV, is found by taking the square root of the variance, and the square root of the variance is a standard deviation throughout the nation. So the standard deviation of the DRVx is defined as simply the square root of the variance, right? So once you can work out the variance, the standard deviation is very easy, guys. That's why I said they were very similar in how you work them out. And yes, the standard deviation is denoted by sigma, not sigma squared, okay? The variance, where are we? Yeah, sigma squared for the variance and just sigma for the standard deviation, all right? Now, this is pretty easy now. What we're going to do now is we're going to work out the standard deviation of x using that formula that we basically showed you on the previous page, which means we've got to work out the variance and then take the square root of it. Now, fasten your seatbelts. Firstly, we have to calculate the variance, yes. And then secondly, the standard deviation will be the square root of the variance. Now, guys and gals, before we can calculate the variance of x, we need the expected value or mean of x, remember? Because it was the expected value of x minus mu all squared, wasn't it? Yes, so we've got to get mu first before we can do anything. So that's first cab off the rank. Right, now, so the expected value of x is the sum of all these specific values of x multiplied by their respective probabilities. Okay, you know how to do that because we've done that before. So in this case, we've got two values of x. We've got c and we've got minus c. So we have to take c, multiply it by its probability, and add to that negative c multiplied by its probability. And the sum of those two terms gets us the expected value of x, which is 0. All right? That's the average value of x, if you like. The expected value, keep in mind, it's equal to, it just means the average, right? That's what I always do. I go back to that, yes, I'm talking about the average kind of thought. Now, the variance of x is the sum of x minus mu all squared and times the respective probabilities. Okay, so now we can actually work that out, right? So in this case, it's going to be the first value of x minus mu all squared times its respective probability, the probability of that value of x, right, which was that one c, plus the second value of x minus mu all squared times its probability, which was 0.5, all right? Now we're getting somewhere. That comes to, yes, looks like a half c squared plus a half c squared, which is c squared, all right? So that's the variance of x. Good heavens above, and therefore the standard deviation will be the square root of that, which would be that, which would be that. Okay? How are you going to get it? So it looks like the standard deviation was just simply c. That was nice and convenient, wasn't it? But that's the long way. That's the long way of doing it, and you'll very, very seldom be asked to do it the long way. So what we're saying here is that using the definition that you've been seeing over there in the blue boxes on the previous screen or two is not always the easiest way to calculate the variance. In fact, there's a much easier way, okay? Now, this is an alternative way which I want you to learn and learn very, very well. The variance of x is equal to the expected value of x squared minus the expected value of x all squared, okay? That's what you need to have seared into your BIOS, okay? Well, just learn it, okay? That's what it is. The variance of x equals the expected value of x squared minus the expected value of x all squared. And we're going to show you how this works. This is really, really cool. Have a look at this. We already know from the previous video on the measures of centre of DRVs, we went to great pains to show you this, that the expected value of a linear function of x, aka this thing, is equal to the linear function of the expected value of x. If you don't know what I'm talking about, go back and have a look at that video and you'll see, okay? But we do know that. We proved that. We proved it beyond any shadow of a doubt with a biased coin tossing scenario exercise in that video, okay? So you have to accept that as is for now, if you don't mind. All right? That's the first thing. Now, I also popped on you in the last video on the measures of centre that this was the case, although we didn't do anything with it in that video, but the expected value of the sum of two random DRVs, different random variables, is equal to the expected value of the first one plus the expected value of the second one, okay? And we didn't prove that or anything, I just popped it on you and then we just left it high and dry and didn't do any work on it last video, but I did mention it, alright? Now, hence, have a look at this, have a look at this. The variance of x is according to this, our definition in the blue boxes on the previous screens is this. Now let's just play with that a little bit and expand that out, alright? And we could say, alright, that's the expected value of x squared minus 2 mu x plus u squared, just expanding out this, yes? In a traditional quadratic manner. Now, what we're going to do now is we're going to say, alright, well, because of this beastie up here, because of this principle up here, right, these are three different random variables. So we're going to say, well, that must be the expected value of the first one plus the expected value of the second one plus the expected value of the third one in accordance with this principle that we found here in equation 2. All right, now the plot thickens and we're going to have a little play with that now. So that equals, first term doesn't change, but you can pull the constants out the front. So you can say, okay, I'll take this minus 2 mu out the front because that does not change the expected value of what's in that bracket, okay? You only have to worry about the variable terms here when you're working out the expected value, and you can pull the constants out the front just like this, yes? Okay, minus 2 mu times the expected value of x, right? That would be the same as that. If you don't believe me, you try one and you'll see it is, all right? Now, this one here, the expected value of just a constant, well, the constant doesn't change, so therefore the expected value of something that doesn't change at all must be just whatever it is. Okay? Does that make sense? I think so. Now, where does that leave us? This is looking very, very interesting now. Now, look, have a look at this term here. What is the expected value of x? What is the symbol for it? Yes, it's mu. You knew, didn't you? Mu. Yes, so it's expected value of x squared minus 2 mu times mu, or 2 mu squared, plus mu squared, my goodness. And these, you can collect the like terms, and we're nearly there, guys. We're a whisker away. There it is. There it is. Okay. The expected value of x squared minus mu squared. And that is, mu is the expected value of x, so that is our formula. Da-da-da-da, ba-dumpch. I know. It's great. Yes? Makes you feel good. So therefore we've got it. Okay, there it is. There's our formula. We've proved it. Now from now on, guys, you've got to remember that very, very, very well. Okay, you'll need it. I'm telling you, you'll need it. It's your passport to success in these DRV thingies. Yeah. Now, a useful property of variance, apparently, which I can't think of any reason you'd want to know this, but we're given it, so I'm going to tell you what it is. The variance of some linear function of x, which this is apparently a squared times the variance of x, where a and b are constants. Now, I don't know where that came from. I don't know how to prove it. I'm just reproducing it for you so that you can just tuck that one away in your memory banks as well. In fact, there's an example here where we're going to use that, all right? So, look, if x is a random variable such that the variance of x is 9, find the variance of 3x plus 2, all right? So there's your ax plus b, where a is the 3, so a squared would be 9. So according to that little formula up here, the answer to the var of 3x plus 2 would be 3 squared times the var of x. Okay, that's what it would be. And the var of x, we're told, is 9. There it is, 9. So therefore we are talking about the var of 3x plus 2 would be 9 times 9, which must be 81, I presume. Very good. Okay, what about b? Fills us with glee. Now this is actually the variance of minus 1 times x, plus there's no b term in there. Okay, so that's the a term here, according to this formula here, would be minus 1. So therefore the variance of minus x would have to be minus 1 all squared times the variance of x. So it would just be that, wouldn't it? Which would be 9. Yes? Okay. Now, as I said to you, I don't really see where you are likely to need that, if ever. But if I was you, I would just write it on your formula sheet that you're allowed to take into an exam, and just remember it if you can, if you've got a good memory. Otherwise, just leave it on your formula sheet, because I've never ever seen it appear anywhere in an assessment situation. But not to put you off, there's always a first time. Now, the interpretation of standard deviation. Yeah, now this is interesting. Look, my take on this is that I've always learned that the standard deviation means it is the average deviation from the mean. That's what it's the average spread from the mean, okay? Yes, but what they're saying here is that it would make the standard deviation more meaningful if we could give it an interpretation that relates to the actual probability distribution. Now, what does that mean, Wolfman? I will show you. It can be shown that for many random variables, about 95% of the distribution lies within 2 standard deviations either side of the mean. Now that certainly occurs in the normal distribution, which we will be dealing with down the track. That's an example of a distribution of a CRV, a continuous random variable, all right? We're doing DRVs at the moment, discrete ones, yeah? Now, in general, guys, okay, the probability that a random variable falls within 2 standard deviations of the mean, that is the mean down to less than 2 standard deviations from it, or the mean plus 2 standard deviations from it, the probability that the DRV will fall within that range of whatever that is and that is about 0.95. In other words, there's about a 95% chance that it will fall within that lower extremity and that upper extremity. Okay, that's what they're saying. Now, this example here, I think personally, guys and gals, is very dodgy. I'm saying that. I'm giving you my disclaimer at the outset, but you wait till you see at the end, and then I think you might agree with me. But let's go with it and let's see what they're saying. The number of chocolate bars sold by a manufacturer in any month has the following distribution. Okay, this is a DRV, right? that's the value, or is this the number of sold? Okay, the number of sold in a month, okay? 100's got a probability of 0.05 and so on, right up to 400 having a probability of 0.05, and presumably that all adds up to 1. I certainly hope so, otherwise we're in a bit of trouble here. So what is the probability that x takes a value in the interval from mu minus 2 sigma up to mu plus 2 sigma? Well, you look at that and you think, well, ye gads, how am I supposed to do that? Well, look, it's very easy actually. First of all, you've got to work out what mu is. That's the expected value of the number of items sold per month. Yes. Then we need the sigma bit. So therefore, we need it to get that. We'll go with variance. Okay, the variance. And then we'll take the square root of the variance to get the standard deviation. Then once we've got sigma and mu, we can work out mu minus 2 sigma, we can work out mu plus 2 sigma, and then we've got a range within which we've got to work out what the probability that x would fall within that range would be. That's the idea. So if you didn't get all that, look, just take it step by step. First of all, work out mu, then the variance, then the sigma bit, right? That's what we'll do. So we need to know, yes, what the values of mu and sigma are so that we can calculate the lower and upper limits of that thingy there, yeah? There. All right, you get that? Now, how do you work out mu? Come on, you know, don't you? Yes, of course you do. The expected value of x, isn't it? So it's the sum of all the values of x times their probabilities, yeah? There it goes. So here we go. So there's the expected value of x. Now, what is it? It's 100 times 0.05 plus 150 times 0.15 plus blah, 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 plus 400 times 0.05, right? That's what that is. Now, that apparently comes to 225, all right? Now, guys, in order to work out our variance, do you remember that formula that I just gave you back there, that nice convenient formula for variance? What was it? The expected value of x squared minus this beastie all squared, minus this expected value of x squared. So in other words, we've got to work out firstly the expected value of x squared. So how would you do that? Well, it would be 100 squared times 0.05 plus 150 squared times 0.15 plus blah 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 plus 400 squared times 0.05, wouldn't it? Now, what on earth does that come to? Fortunately, I had worked it out. So apparently it comes to 55,000. Yes, I know. Don't worry. We'll get there. Now, over the screen. Now, where are we up to? Recapping. That's a good idea. The expected value of x was 225. The expected value of x squared was 55,000. So I think we can work out the variance now, don't you? Let's go with that. Wow. So it looks like it's 55,000 minus 225 all squared, and I have no idea what 225 squared is, but I'm about to find out. There it is. Wow. So what does that come to? That comes to 4,375. Now, what have we just calculated, guys? Well, we've calculated the variance of x. So now all we've got to do is take the square root of that, and we've got our standard deviation, which was what we were really looking for. Okay, so it comes to that. All right. Now, we've got our mu, this beastie here. We've got our sigma, so we can work out mu minus 2 sigma and mu plus 2 sigma. Yes, that's 2 sigma. Therefore, we want that, right? So therefore, we need the probability. There it is. There's mu minus 2 sigma. There's mu plus 2 sigma. And I'm trying to work out that the probability that x would fall between 92.6 and 357.4. All right? Now, with this table, guys, here's where I get all riled up and steamed up and hot under the collar. I don't think you can do that. I don't think you can do it at all. Because how do I work out the probability that x is going to be more than 92.6? 92.6 doesn't even appear here. What am I supposed to do? How am I supposed to work that out? And less than or equal to 357.4, well, excuse me, I don't know how you're supposed to do that, and it's wrong and inaccurate to take it to somewhere just to guess a number in between. However, the powers that be that wrote this question and a worked answer for it said this, which I disown. All right, it's not Wolfman's work; it's somebody else's. So I'm just quoting it for you. From the table above, this cannot be computed. That's Wolfman speaking, because 92.6 and 357.4 do not appear in the table. The rest of it is the worked answer in the text. However, the probability that x is greater than or equal to 100 and less than or equal to 300, well, I mean, how did they arrive at those figures, I ask you, equals 0.95? Well, yeah, but 100 is not 92.6, and 300 is not 357.4, but that's what they did anyway. So they said, therefore, the probability that x lies within that point there and that point there, aka 92.6, 357.4, they're saying it's kind of round about 0.95 as a general rule. Well, I'm sorry, but I don't see that, you know. Fortunately, guys, you wouldn't get a question like that in an assessment situation where you had to get all kind of furry and blurry and try and guesstimate it from some values which are nearby. It just isn't going to happen, all right? So just rest easy. But the whole principle of this exercise was to try and relate the standard deviation to the context of probabilities within the probability distribution, right? And they often quote the probability of something being within 2 standard deviations either side of the mean, that kind of thing. And that's the context that they're trying to get you to sort of think within in this DRV example, okay? But it just doesn't quite work with a DRV example, as I've been saying. But anyway, you get the general drift, don't you? Yeah. All right, I won't go on any further. I think we'll just finish there. Yes, well, that's what they say, although I don't quite agree. And you're a star. Huzzah! And you will go far, providing you go and learn those formulas and do some practice of this stuff. It's really quite friendly. It really is. But I do want you to remember that the variance is, what is it? The expected value of x squared. It's e of x squared minus e of x all squared, right? And the standard deviation is the square root of the variance, all right? And just a general idea of that blue box formula would help. The variance is, what is it? The expected value of x minus mu all squared, right? Which means you've got to get all the individual values of x minus mu, square them, multiply them by their respective probabilities and add all that up, and you will get the variance. Yes, that's how you do it. All right, I'll see you next time. Have a wonderful day, and thanks for being with me.